which is titled The Tale of Flexibility, Generalized Average for Hyperparameter Tuning and Pooling. It sounds very mouthful, but by the end of this presentation, you should be able to unpack every single element of this title and hopefully use it for your own advantage in your own projects. The idea for this presentation started when I visited Uri. Uri is here. You will see him in a second. In Haifa, and we went to eat some hummus. So we finished the first portion, and then we wanted some extra. And we asked ourselves a question that supposedly is a question that is too basic even for an entry-level data science interview. And the question was, what is an average? My name is Aleksander Molak. I'm an educator and speaker at Lespire.io, machine learning engineer and researcher at Ironscales. I love traveling with my wife. I like languages, running, and I love good vegan food. I'm also working on a book on causality in Python. If it's interesting for you, you can scan this QR code or go to causalpython.io. And with me today is Uri Itai. He's a mathematician holding a PhD from Technion, algorithm developer, data scientist, loving combining all three areas together, and he loves meeting new people. So do I. So if you want to reach out after the presentation, don't be shy. And this is a joint work with Nathan Katz, our friend from Tel Aviv. He's a data science leader, researcher, master's in physics from Weizmann Institute, and he loves combining theoretical and applied aspects of machine learning. So what we're going to learn today are three generalizations of the average, of an average, I should say, how you can use this the concept of generalized average for machine learning projects to make them better, and in particular, how you can make use of general average in graph neural networks. So our goal today is to give you all those tools so you can take them and apply for your projects, and also give you a theoretical understanding why what we think an average is just like a very special case of what an average is in general. So we want to try to give you this tool also so you can see the average in all its beauty. Agenda for today, we'll start with the question, what is an average? We'll discuss types of averages and their basic properties. Then we'll talk about the concept of general average. So we'll talk about a couple of averages, and we'll try to generalize this concept. Then we'll show how this can be applied for goodness of fit. So for instance, when you're tuning your model, tuning hyperparameters of your model, then we'll show you a little bit of our research with graph neural networks and show you how generalized average operator can make your models better. And we'll quickly summarize. So what is an average? And I'm passing the microphone to Uri.
Okay, what is average? Maybe it's the most simple thing that everybody knows what is an average. And so we start ask GPT. An average is set in tendency, which a way to describe a set of data and other stuff that nobody really understands what's their meaning. So what is it? So what does it mean? By all means, what does it mean, being mean? And don't be mean. It's okay, let's type of average. In junior high, in elementary school, we learned the arithmetic mean. I know my son is in 8th grade and he learned about that. In high school, you learn the geometric mean. In calculus, you start the harmonic mean, which is the arithmetic, the inverse of the arithmetic mean of the inverse. And so there's more than one type of an average, and actually there's 25 different types.
I think given 28.
28, and well,
that we know of.
Actually, by the end of this lecture, you will know that there's a continuum of averages. So this number 25 is a little bit is too small. Okay, ignore the x-axis and let's see we took the harmonic geometric mean of this array, and we see that the harmonic is always the less one of them. The arithmetic is a maximum, and let's see how does it scale when we're a little bit playing with the numbers.
Yes, and just to add one more thing, these gray lines on the bottom and on the top, they are minimum and maximum of this array, right? And then in the middle, you can see all three averages, as Yuri said. And an important thing is to ignore the x-axis for now, okay? But you will see that this makes sense. And now, as Yuri proposed, let's see what happens when we increase the variance of this array, but by adding smaller numbers.
Okay, so we took one, and we see that the arithmetic mean is about the same. The geometric mean is a little bit further down, but still stable, and the harmonic means drop down. That's an interesting thing. We don't have the time, but if we add the variance to an upper, we won't see this phenomena. Okay, so what is an general averages? And okay, everybody studied calculus, the mean inequality. We say that the average of the arithmetic is less than the maximum. It's more than the geometric, more than harmonic, just like we saw, and more than the minimum. And there's equality only in one case, when the array is fixed, and we know that.
Which means that all the values in the array are the same value.
Yes, fixed. Okay, and now here's our maybe little bit something that might be scary at first glance, but don't be afraid. We defined a function which is called the p function for all values different than 0. P would be the pth root of the arithmetic mean of all the elements in the p power, and for 0 it just would be the geometric mean. And obviously for a positive number, this is we program it. It's, you see, easy code. Even I was able to code it, so it's not that hard. Each one of you can. And see that this is just this formula, and things that we got to be careful. First of all, it's differential. The differential, as probably all of you know, allows you to coordinate optimization process, and everything is much smoother and easier than thick. The second thing that we want strictly positive in each component. If it's even strictly positive in P, but it's a different story. And we get another interesting phenomena that it lies between the minimum and the maximum. If you go to minus infinity, you get the minimum, plus infinity, the maximum. -1 harmonic mean, 0 obviously is a geometric mean, and 1 is the arithmetic mean. Okay, we can use weighted averages. Till now we didn't mention weighted. We'll go further that, but it's a big thing in machine learning. And the second thing which is important is that if we do reordering, we'll get the same values. And this morning we talked about things should be commutative, so we get that. Can we rewrite more? Can we rewrite more stuff? So actually we can do more. And there's the Lermer, which is an American mathematician, and he just took the arithmetic mean of the p power divided by the arithmetic mean of the p minus 1. And this function it is a function. It is agreeing with the law of the previous slide, Lermer, and is another feature of those means that was our condition, that everything got to be very easy to implement, because otherwise you can get full, and you get full and get too messy, and so everything here is a few lines of code. So if anyone is interested in using it to your own project, don't be afraid. It's easy and fun. Okay. It is differential, which is good. It is strictly monotone in all components, including P, and it's agree with the minimum. Again, the minimum P equals to minus infinity is the minimum. Plus infinity is the maximum. 1 would be equals to the arithmetic. Half is going to be the geometric, and 0 is going to be the harmonic. But
Yeah, and as you can see, these are exactly the same conditions as we've seen before for P function. So you can see that although the formulas for lemma mean and for P average were different, they meet the same criteria and the same conditions. So now let's see how this can be translated to something a little bit more visual and a little bit less abstract. And hopefully we'll start getting into a place where you can see, where we'll be able to see how this can be useful for you in machine learning projects. Okay? And one more, your favorite
yeah.
tip,
If
right?
we're taking P equals 2, we're getting the coharmonic means. If anyone of you has done signal processing, it's a mean that people in signal processing love. So it's got related to that. If you never did anything like that, just know that you can take this part into signal processing. That's it. Okay, P is a real number. From minus infinity to plus infinity, it moves freely from minimum to maximum. It's conserved preference of conservative liberal. What does it mean? Conservative wants to be cautious, so he wants to consider the worst case scenario. So he wants to take lower value. And a liberal would go for the best case scenario or the average scenario. And so basically you can choose your conservative liberal preference according to your use cases. In some cases you prefer just being good in one aspect, and that's fine. And in other, you can screw it up. Like say you're in the security sector. You have no room for any errors, and maybe you're doing algo trading and you just need to be good in one component, and then you hit the jackpots. And here again this array, and the interesting thing that we plot the P average with various values of P in the Lerman. You can see the S shape. We didn't implement that as an activation function, but can be a nice homework. And we can see when we change the variance of the array with a lower value, we can see that the S is more shaped.
So it becomes more steep. And also another thing that you can see here is that lemma is in general more steep in both cases, right? So it grows faster. But also, as you can see, as we discussed before, the minimum value is never lower than the minimum in the array, and the maximum value is never higher than the maximum of the array. Yeah. Okay, so this property holds here. And also, you can see how those lines are crossing the horizontal lines, right? So geometric, harmonic, and arithmetic mean, you can now see that they are just special cases of lemma average and P function.
Yeah. And yeah, this is exactly spot. Okay, so till now it was a nice math exercise, but we're doing a machine learning workshop, so we got to enter here. What is a generalized F1? F1 is we're taking the harmonic mean. We can replace with general average, because F1, as you probably recall, is just the harmonic mean between the recall and precision, and it can be, and everything can be applied with weight. So if you have some kind of preference, you get it. Average and goodness of fit. Okay, just like we said that this is the harmonic mean of the recall and precision. And there's the F beta, which is the weighted. Beta equals to 1 is the equi-weight.
Mm-hmm. So let's just add one thing here so we discussed this P average and lemma. Both are generalizations of average in general. And now we are seeing F beta score, which is a generalization of F1 score by weighting F1 score. So generalization of harmonic mean in particular.
Yeah, exactly. For large beta means that the large, we will see next slide what does mean large beta and low betas.
Yeah, but in general you can use the F beta to penalize your false negatives or false positives more. So for instance, if false positives from your business point of view or machine learning project point of view are most costly for you, you can use this function to penalize them more. On the other hand, if false negatives are more costly for you, you can use the same function with a different value of beta to penalize them more.
Okay. Okay, and this is the we optimize the parameter with different with the f beta. This is and beta equals to 3 in our case, where it's a down precision, which means less false negative. If we're taking low beta, it would be vice versa, no problem. And this is the graph when you about the recall and precision to possible values, and we see this is kind of a reflection of the same graph, and higher beta and closer f to recall.
So the higher the beta is, the closer we are to recall, regardless if recall is higher or lower value, okay? Which means that we always penalize false negatives harder in this case. And that's why, because false negatives are a part of the recall equation.
Okay.
And the horizontal line is F1 score, like traditional F1 score. So you can see again that these lines are crossing at some point. This point is at 1. And this shows us that F1 score is a special case of this F beta score.
And actually, and you can take one thing further. Instead of taking the harmonic mean, just like here, you can recall that the harmonic mean is a p function with value p minus 1, or the Lehrman with value p equals 0. So you can do all the analysis here with those two general functions, which gives you another degree of freedom to choose your favorite metric. Okay.
Okay, beautiful. And then we go to GNS. Okay, so now I need to ask you for like an ultra laser focus, because for those of you who are not familiar with graph neural networks, we'll do like a very, very quick overview. Let me ask you, who's familiar with graph neural networks? Who have some experience with GNS? Okay, so a couple of people have. Okay, good. So we will do a quick recap first. So what are GNS? GNS, or graph neural networks, are neural networks that operate on graphs. So the name is informative. They leverage graph structural information, which means that when we train a network like this, we do not only look at the features of nodes or points or data points, we're also looking at their properties, structural properties, how they are connected with one another. Okay, so maybe in my cell phone there, I have Uri's number. Okay, and this would constitute an edge between me and Uri. What's your name? Matthew. I don't have Matthew's number, so we don't have an edge. Okay, we are nodes, all nodes, and only Uri and we are connected. Are you connected with Matthew, Uri? You are. So, okay, so this is like a missing edge to form a triangle, so-called. Good. So now, let's imagine this graph. We also have, this actually perfectly describes the situation. So, I will say that A is me because I'm Aleksander. Maybe Matthew, no, Uri is here, and Matthew is here, right? We have some properties. So, each of us, Matthew and Uri and I, we can all be fully described by just 3 numbers. Surprising maybe, but let's assume that's true. So now we will say a thing like this. Okay, A, B, and C. This just says like A is me on a node with in this graph. B is Matthew and C is Uri. Sorry, the other way around. Uri and Matthew. And now we want to train a neural network that will predict something about this graph. But we want to preserve the structural information. So to do it, what we do is we take the information about the node itself, take the information about the neighbor of this node, and we pass this information through some function. For now, let's say it's an arbitrary function. And we do this for each of the nodes. Okay? But as you can see, for node A, I'm not taking into account the information from node C. Okay? It's only nodes A and B. For node B, I take information from all of those nodes because it's neighboring with both A and C. Now, an important property of this function, whatever it is that it is permutation invariant, which means that if we reverse the ordering of these vectors, the output of this function is the same. It doesn't change. So that's the reason why people use average and sum in graph neural networks very often. So now when we want, at some point we train this neural network, and at some point we want to get a graph level output, so maybe we want to predict what this graph is. Or maybe we want to predict a number that will be called a graph regression. So maybe we want to predict what is the total waiting time on a certain, in a certain area of the city when you have pkakim, like a traffic jam, okay? Or maybe we want to predict if a given protein that is represented as a graph belongs to one of 5 or maybe 7 classes. So here is a visualization of a protein, and this is how we can map it to a graph. This is 3-dimensional, but it doesn't matter. So an example of a graph level task can be take a graph with information about its nodes, where the whole graph represents a protein, and find a label for this protein. So maybe it's a class 1, 2, 5, or 7. I don't want to go into biology. And how we do it, we again use some function that aggregates all of these representations. And this function also needs to be exactly permutation invariant. Very good. And this function is usually called global pooling. Okay, so we're pooling all the information from the graph. And if you have an association with CNS or computer vision, that's a very good association because graph neural networks are a generalization of convolutional neural networks. So although this might be slightly different in detail, the idea is it's the same idea. Okay, and what we do, we take this representation, we pass it through some dense layer with softmax, and this is how we generate a label, a prediction. So now we run an experiment. We thought like, okay, so our generalized average operator is permutation invariant as well. It's not as symmetric as mean is, but it's also differentiable. So this parameter P, we can put this parameter into a neural network and optimize it jointly while learning the weights for the network. So we use GCN architecture. We also tried GAT, but we are presenting GCN today because it's a little bit simpler. We used proteins data set, which represents proteins as graphs. And for each graph, we want to predict a label. We had like 5 different treatments, which were 5 global pooling conditions. We used average, sum, max pooling, and 2 times lemma mean as pooling operator with 2 different initializations. So we started with different values of P in the beginning, and then we were optimizing from that moment. We ran 100 runs per condition, and this is how we do it. We use TensorFlow and Spectral for this. So this is our class, global lemma pooling. We use GCN convolutional layers from Spectral, and these are the results. So you can see accuracy here. And we need to say that we were not optimizing this architecture for very good results. You can get much better results in general. We're just caring for the comparison of the operators. Here you have sum operator. Here we have average, like regular average. This is lemma mean with initialized with parameter 1, which means that we initialized with regular average because lemma mean with P1 will give you just like a regular mean. Then we have lemma with value 10, which is very close to maximum. It's not maximum, but it's very close to maximum. And then we have max pooling, okay? So for each of those representations for 3 numbers, we are taking max in each dimension. We are taking lemma with P10 for each dimension, average for each dimension, and sum for each dimension. And what's important is that sum, we know that sum gives us a graph neural network that is the most expressive possible according to so-called Weisweiler-Lehmann test, okay? Maybe some of you are familiar with this, maybe not, but this means that it gives us, as far as we know as of today, it gives us the highest possible theoretical expressiveness of the network. So let's see this in numbers. Maybe it will be a little bit easier to compare. Average was giving us the smallest accuracy. Lemma 1, which was starting from average and then letting the network optimize, was slightly better. Maximum was slightly better than Lemma started with parameter 1. Sum was very good. And Lemma started with parameter 10, close to maximum, and then going down. We will see this in a second. Was even better than sum. But this is very close. And you will see that this result was not significant statistically. So we were able to match. Able to match performance of sampling that is gives us the highest possible expressivity with our operator, and do better than anything else. And here you can see this is for Lemma for a network started with Lemma with p-value of 10. You can see how it was optimized. You can see that it goes down, not very much, to 984 or something like this, but it goes down consistently over different trials. And you can see these spikes going up at the end. And this network was trained with early stopping, which is a strategy of stopping the training when the network is overfitting. So all those spikes going up were going up like after we had the optimal score. Okay? So this means that the spike is also indicative of overfitting in the network. Challenges and next steps. So first thing, we had some challenges with numerical stability for the p parameter when training a graph neural network. We want to try normalizing p in order to get more efficient optimization, because for now we were just using like values like 1 and 10, which comparing to most of the weights that are normalized somewhere on the way, these are very, very high values. And we want to integrate this operator with Spectral, which is a graph neural network library built on top of TensorFlow 2. Summarizing. Average can be generalized in various ways. So we've seen 3 ways today. One was p-average, another one was Lemma mean, and another one was f-beta score. Generalization can help you achieving specific results in hyperparameter tuning. So for instance, you might penalize false positives or false negatives, depending on your use case, more using this average. And Lemma average matches or exceeds the performance of most popular and most expressive operators used in GNNs nowadays. Yes.
And the main thing between till now, f-beta is kind of a weighted average that I guess some of you know, but it means that you know what's your performance, recall or precision. And both the Lerman and the p-value, you just say what you prefer, minimum and maximum, which you have no prior knowledge which one is going to be the minimum and the maximum. So we believe that combination of both the weighted and the generalized average is going to be very useful in machine learning. And go and use it on your project. We'll be happy to help you.
Yeah, great. Thank you so much. And I guess we have 5 minutes for questions. We have 5 minutes for questions, so we're very happy to take your questions if you have any. If the concept of feed-forward attention is not popular in graph neural networks. Concept of attention in general is very popular in graph neural networks. Feed-forward, that was the paper.
So it's like a weighted average with the weights revealed there?
Yeah.
Not compared?
Yeah, so we haven't compared this so far, yeah. Does it answer your question? Yeah. Okay, I think it's a great suggestion.
Either, though, I think it's important.
Yeah. That's a great suggestion. So we will continue the experiments with attention networks and all the attention. Yes?
I speak loud enough.
Beautiful.
You showed an example. We have an implementation of your function that you actually use in code. Is it something that you intend to expose in open source? Is it already implemented?
Yeah. We have some of it.
Let's talk, because for the recording. So the question was that we've shown an implementation, and Yaakov asked us if this is something that we are willing to open source, and you always said that yes.
Yes, actually, we do have already a PyPel library. We're working on that, and hopefully it's going to be to your friends in scikit-learn, but they're doing lots of problems. If anyone wants to use that, we'll be happy to give you our own model and just to pip install it and enjoy.
Yeah, so the package is still in beta, but we'll be announcing this soon. Thank you.